So today we're going to be calculating an independent samples t-test. There are 5 steps. You're going to use the worksheet, that is the PDF, and you can follow along with the 2 examples that are given in the Prezi lecture. I will be posting other samples for you to work through if you choose to do that. There are 5 basic steps. The first thing we're going to do is define our null hypothesis, determine what our critical region is going to be. We're going to fill in the information that we have from the example. The second step is we're going to calculate the pooled variance. Following that, we're going to calculate the estimated standard error. Once we have the estimated standard error, we're able to calculate our value of t, and based on our t that we obtain, we're either going to reject or fail to reject our null hypothesis. And then finally, we're going to calculate our effect size. So for right now, I'm going to cover up this half so that we can really just focus on what we're doing. So when we're talking about independent samples t-tests, the definition for the null hypothesis is always going to be exactly the same. We're assuming that these are 2 completely unique different populations, and our null hypothesis would suggest that these 2 populations, if you take the population means from each other, you would end up with 0. Our alternative hypothesis says that the 2 population means when subtracted from each other would be something other than 0. Remember, when we're calculating an independent samples t-test, this is an example where we have 2 samples. We do not have any population parameters. Therefore, we don't know what the population means and standard deviations are. We are going to make estimations for those, but we're still able to calculate whether or not a difference exists within these 2 groups. We need to calculate our degrees of freedom so that we can know what our critical region of t is going to look like. The critical region is always calculated by obtaining the degrees of freedom first. So for our example, the degrees of freedom for group N1 is going to be 8. Our degrees of freedom for N2 is also 8. So 8 plus 8 is 16 minus 2, so our degrees of freedom are going to be 14. It's really crucial for us to know what our degrees of freedom are, because unlike when you're doing a z-score, the t critical region is based on the number of individuals in the sample. So at this point, I'm going to get my t distribution sheet. I'm going to look down until I find degrees of freedom 14, and then I'm going to look all the way across until I see portion in 2 tails combined of 0.05. So it looks like my critical value of t is going to be 2.145. So a t with degrees of freedom of 14 is going to be 2.145. So later on, when I calculate my t-score, I'm going to compare it to this critical value of t. And if I get a value that's higher than this, then I'm going to reject my null hypothesis. Remember, the t distribution is normal. It looks like this, right? And I can either get 2 tails. So in truth, either I would get 2.145 or negative 2.145. And if I obtain a value in this region or this region, that would lead me to reject my null hypothesis. Filling in the information for the example, for sample 1, n is 8. The mean of sample 1 is 72. The sum of squares is 480. And then calculating my degrees of freedom for sample 1, which is just going to be n minus 1, I'm going to get 7. For sample 2, n is 8. The mean is 61. The sum of squares is 456. And the degrees of freedom are also going to be 7. So I've filled in all of my basic information, and now I can begin calculating my value for t. So the first thing I need to do is calculate my pooled variance. Pooled variance, if you remember, we were doing this for our z-score was s squared p, and the formula for that is sum of squares 1 plus sum of squares 2, all of that divided by degrees of freedom 1 plus degrees of freedom 2. And you may be asking, why do we need to calculate the degrees of freedom separately? In this example, the ends for both of our samples are exactly the same. They happen to be 8, but most of the time when you're doing research, you are going to end up with groups that have different sample sizes. So now I can simply fill in the values from the information that I have. So sum of squares 1 is 480, sum of squares 2 is 456. The degrees of freedom 1 is 7, degrees of freedom 2 is 7. So this is going to give me 936 over 14. And if I do that division, I'm going to get a value of 66.85. So now my pooled variance is 66.85. I can go on to step number 3, where I calculate my estimated standard error. You can see estimated standard error is written as S M1 minus M2, and the formula for that is the pooled variance over N1 plus the pooled variance over N2. You take those two, sum them, and then you take the square root of that. And again, it may seem straightforward when your sample sizes are equivalent, but there are times when they're not going to be, so it's important to follow all the steps. So this is simply going to be 66.85 over 8 plus 66.85 over 8, and that's going to be 8.35 plus 8.35, and if I add those two together and I take the square root, it's going to be equal to 4.08. I'm simply skipping the calculator steps. So now that I have my estimated standard error, I can go ahead and I can calculate T. So here is my formula for T. T is equal to M1 minus M2 minus, and this is the part that's a little bit strange, mu1 minus mu2. Now we know we don't actually have these population parameters, and so in this equation we're always going to make the assumption that that value is 0. And then we're going to divide by our estimated standard error. So M1 is 72 and M2 is 61. And you can see how in this case, if you had samples where, this ended up as a negative number, that's just fine. Again, T has a normal distribution, and so we're going to either reject or fail to reject based on whether or not our version of T falls in these critical regions. It can be positive or negative. The sign really makes no difference. It's really the value. And then we're going to divide by our estimated standard error, which is 4.08. And so this is going to be 11 divided by 4.08. And in this case, our T ends up being 2.69. So now we need to determine, are we going to reject our null hypothesis that says that these two populations are essentially the same and therefore there's no group difference, or are we going to, that would be fail to reject, or are we going to fail to reject our null hypothesis? We make the determination of whether to reject or fail to reject based on the value of T that we obtain. If our value of T occurs in the critical region, then we're going to reject our null hypothesis. We're going to say it isn't the case that these two populations are the same. These two groups are different from each other. And so again, our T critical value that we obtained is 2.145, and a value of 2.69 would fall, right about here. And in this case, we are going to reject our null hypothesis that says that these two groups are the same. We're rejecting that, therefore we're assuming that these two groups are in fact significantly different from each other at the p less than 0.05 level, because that was the alpha that we determined. So I can write that in here, alpha equals 0.05. We're always going to use an alpha of 0.05 in these examples, but it's a good thing to make sure to include. So finally, our last step, we're going to calculate our effect size, because if you remember, there are cases where we could reject our null hypothesis. We could state that these two groups are significantly different from each other, but it could be a very small and therefore a meaningless difference. So it's important for us to calculate our effect size. And if you remember that it's an estimated Cohen's D, right? Estimated D. And the formula for that is simply M1 minus M2 over the square root of our pooled variance, right? This would essentially be our pooled standard deviation. In this case, it's going to be 72 minus 61. We're going to go back to our estimated standard. I actually hadn't, so it's going to be the square root of 66.85 here. And in this case, it's going to be 11 over 8.17. And in this case, it's going to be 1.34. And down here, I did include some cutoffs for you to be able to determine whether or not your estimated effect size, your estimated D, is a small effect, a medium effect, or a large effect. In this case, it's quite robust. So it does seem like, based on our example, there's a very significant group difference. So these are all the steps that you need to calculate a T, define your null hypothesis, set your critical region, include all the values that you've been given, calculate your pooled variance, calculate your estimated standard error, calculate your T, determine to reject or fail to reject, calculate your effect size. If you have any questions, you can certainly reach out to me for an email.